All right, so as an introduction and a general overview about the way we store data in Scylla and the way we compact it, I'm going to talk about log-structured storage and then the fundamentals of compaction. So first, what is log-structured storage? How do we use it for writes? So we start with changes to the data that are coming down the wire over CQL, usually. And the first thing we do with them is we record them in memory, in what we call memtables. We also store them in a write-ahead log, what we call the commit log, but that's a little bit out of scope for this presentation, so I will not talk about that. But the next interesting step is we flush the data from the memtables down into SSTables. And then updates to the data accumulate over time across these SSTables. So say we wrote, I don't know, A to some cell. It will be recorded into one SSTable. And then at a later time, we write B. Then we may have a write of A in this SSTable and a write of B in another SSTable. And we need to take that into account. Now, having several versions of the same cell being stored is called write amplification. The SSTables themselves are immutable, meaning they are written once, and they are never rewritten. They contain the changes to the data that we also call the mutations. Another aspect of SSTables is that they are sorted, and this is where they got their name from, as sorted strings tables. And they also have, in addition to the actual data, they have metadata like index, statistics, and filter data that allows us to query the data efficiently. Now remember, as a note, that there is no static view of the databases. So unlike, say, relational databases that keep the actual information in tables on disk, we only keep the changes to the data. That means that for reading the data, querying the data, this requires reading all the relevant SSTables that may contain pieces or updates to the data. And then we apply those live mutations, those mutations that are not TTL'd or not overwritten by other mutations. We apply them onto our cache, and that's the way we get the form, the final form of the cells, the rows, partitions, and so on. Now we use the Bloom filter to locate the relevant SSTables. Now doing this consolidation process, consolidating these mutations, is pretty expensive because we need to access the data, access the disk several times, and do the consolidation in memory. And this is called read amplification because we will need to read multiple SSTables in order to form like a single row. So to summarize, why is compaction needed at all? So first, to reiterate, SSTables are immutable, and we can't just keep writing updates onto this. The disk will just fill up. And we have to get rid of obsolete data. That means data that was explicitly deleted, or it was expired using TTL, or it was just overwritten. We still need to get rid of the overwritten data. So we need compaction to reduce space amplification. Then the data itself may be scattered around in different SSTables, and we would like to consolidate it to reduce read amplification. So let's go over the fundamentals of compaction. So the first step for compaction is to select a set of SSTables to process. The algorithm that selects these SSTables is part of the compaction strategy. So different compaction strategies may have different selection criteria. Then compaction reads these SSTables and writes the compacted output onto a new SSTable. Remember, SSTables are immutable. We never rewrite them. So we have to write a new SSTable, which is the compacted output of those input SSTables. And while doing so, we eliminate all the overwrites, all the deleted data, and the expired data. Eventually, when this output SSTable is sealed and safely stored on storage, we can finally delete the input SSTables. Okay. Note that doing this compaction requires temporary space because we cannot delete the input SSTables until the output SSTable is safe on storage. So during compaction, we will have on disk both the input SSTable and the output SSTable. So what can we eliminate during compaction? Let's go over a few examples. So say one SSTable has a write of A into some cell, and another SSTable has A prime, which is a newer version of the same cell. In this case, we just have to keep A prime, which is the newest content for this cell. If we only have one update to the cell, we just copy it onto the output SSTable. If we have data into a cell and not C represents a tombstone, a deletion of this data, we still need to copy the tombstone. And that's pretty fundamental to compaction in Cassandra and in Scylla. We can't just get rid of both the data and the tombstone because this tombstone may need to delete other data that resides on other SSTables that we haven't got to compact yet. So when can we finally get rid of tombstones? Okay, another example for just a tombstone. And the final example, it's this node Z. Node Z represents a droppable tombstone. A tombstone which was already expired. And this way we can get rid of the tombstone and not copy it onto the output. So the tombstones are kept around for what we call the GC grace seconds configuration option. And that allows us to garbage collect other data. And when that expires, we can get rid of the tombstone.